Hey guys, welcome to video 4.1. This is our first video in Unit 4. And Unit 4 is all about forces, which we've been learning about, but instead of just forces in one dimension, we're going to look at forces in two dimensions. So in this first video, what we're going to be learning about is we're going to take a closer look at vectors. Okay, so what's a vector? Well, a vector is just an arrow, and the arrow in our examples today are going to represent force. So, when I ask you to draw a free body diagram, I say, okay, draw the square and then draw all the forces that are acting on that object, right? So these are all examples of vectors. Ooh, that was not what I meant to do. It's way too big. So these are all examples of a vector. So for us, it's just an arrow that's representing force. So vectors have a tail end, that's the part without the actual pointy part of the arrow, and then they have a head end, which is the part with the pointy. So whenever I'm talking about the tail end of a vector and the head of a vector, this is what I'm referring to. Vectors have magnitude. Magnitude is the number associated with that vector. So vectors have magnitude. Magnitude is just the number. So when I ask you to draw a free body diagram and you were to label the forces, like maybe this is friction, this is normal force, if you were to write down a number here, like let's say the normal force is 84 newtons, that is an example of magnitude. Okay, so magnitude is just a number. But vectors don't just have a magnitude, they also have a direction. And that's really important. Which way is that magnitude going? So normal force has a magnitude going north or going up. Or you could say it's positive. There's a bunch of different ways that we can represent the direction of the force. Sometimes I say backwards, sometimes I say downwards, sometimes I use the sign negative. But there's a bunch of different ways we can represent direction. Another way we can represent direction is with degrees. Okay? A degree can tell you which direction this arrow is pointing. So magnitude is represented by a number, and direction is represented by a bunch of different things. It could represent by a degree sign. It could also be like north, south, east, west. It could also be represented by like a positive or a negative sign, or by words like backwards and forwards. So that's what a vector is. Now, one thing we did already learn about vectors is that you can add them if they're going in opposite directions. And so I just want to review adding vectors. Okay, what we've learned about adding vectors is we've applied it to net force. Net force is all your individual forces, individual forces added together. So this formula is going to be different for every single one of these equations. It's going to be different because they all have different individual forces. So this guy's net force for this first box is your tension force plus your gravitational force. Okay. Remember, tension force is going up, so it's positive. Gravitational force is going down, so this is negative. So really what this turns out to be is 1200. That's your tension, subtracted by 800. See how we're adding gravity? But the gravity was negative, so you're adding a negative, which means you're subtracting. So then my answer is 400 newtons. That's my net force. Let's calculate net force for this equation right here, the blue one. So what's its formula for net force? Well, it's got two different forces. It's got air resistance, which is 600. I guess I should write that out first. It's got force of air resistance plus force of gravity. So the air resistance is 600, and it's positive because it's going up. Gravity is going downward, so it's negative. So the net force is negative 200. What does this negative tell me? It tells me that my net force is going downward. Okay, this one was positive, so my net force was going upward. And you can see that with arrows, right? The bigger arrow shows us what direction the object's going to be accelerating. Let me show you this one too. Let's look at this black box. So here the net force formula looks like this. Normal force plus gravitational force plus friction force. So if I look at the values here, my 50 newtons for normal is positive, my gravitational one's negative, and my friction one is going backwards, so it's going to be negative. Okay, and so then I end up with negative 20 newtons. That makes sense because my normal and my gravitation cancel out and I'm left with this, and so it's going in the negative direction. So one thing I didn't tell you when we're writing these formulas is that I told you could just add up all the individual forces together. Well, we're going to now deal with a little bit more of a complicated scenario, in which case you can't add all the individual forces together. What I want you to do from now on when we're looking at a box is I want you to separate the up and down forces and separate the left and right forces. Okay. So when you're writing your formula, let's say this is normal force up here, gravitational force down here. Let's say this is applied force and friction force. So I want you to put a parentheses and say, here's your normal force plus your gravitational force. Put a parentheses. And then in a separate parentheses, put your left and right forces. So this is your up and down forces. And then this is your left and right forces. Applied and friction. So it's important that you separate them because what we're going to deal with now is what I typed up right here. What happens if you have an unbalanced force up and down and left and right? Let's say my normal force was 60 newtons. Let's just say that. Let's say my gravitational force was 65 newtons. Remember, it's a negative value. What does that mean? Well, my normal force and my gravitational force in this particular instance aren't equal. So let's say, oops, I did my addition wrong. So I have a -5 here for my object. Let's go ahead and draw it out. Let's say my normal force was 60 newtons and my gravitational force was 65 newtons. And it's negative. That means the object's going to be falling. Okay, it means it's breaking through whatever it's sitting on. Okay, so let's just say that's happening. Let's also say that my applied force is 20 newtons and my friction force is 15 newtons. Well, 20 plus, remember, friction's negative, it's going the other direction, so plus my -15. What does that give me? Well, over here, that's going to give me 5. Okay, here's what you can't do. If you have an unbalanced force up and down, so this is my up and down force, it's unbalanced, and you have an unbalanced force left and right, you cannot add them together. It just doesn't work that way. So what I want you to do is if you have an unbalanced force up and down, I want you to redraw your picture and show me that force. -5 newtons. Okay? Now here's your left and right force. Show me that on your free body diagram as well. 5 newtons. We can't add them together because they're not going the same direction, right? So here comes in the Pythagorean theorem. Whenever you're given an unbalanced force up and down and an unbalanced force left or right, you have to use the Pythagorean theorem to find what's called the resultant vector. Okay, so if this box is being pushed downward and to the right, we know the resultant vector force is going to go in this direction, right? If I decide I'm going to push this cup of Coke down, but I'm also going to push it to the right, what ends up happening? It's going to go diagonal, right? So if I'm applying force downward and to the side, it's going to be going in a diagonal direction. So you need to calculate what force it's going in this direction. Okay. So the Pythagorean theorem states if you want to find your resultant vector, you just need to take your two vectors, square them, and it equals the resultant vector squared. So for example, let's say here's your box. I said you're going to push it 11 kilometers upward. And you're going to push it 11 kilometers eastward. We know the resultant vector is going to be something like this, right? It's going to go in this direction. So how do I find how many meters I pushed it. Notice we're using meters here, but you can use anything. You can use force, you can use speed, you can use acceleration. This can work for any kind of unit. So if I have, I'm pushing it upward and I'm pushing it to the rightward, how far is it going to go in this direction? So I take these two numbers, okay? You take your two forces, so take force 1 and take force 2, and you're going to square them, okay? And you'll end up with a number. It will equal the square of your resultant force. So right now I have 242 equals r squared. Well, how do I get rid of the square around the r? All you have to do is take the square root. If you take the square root of r squared, it's just r. If you take the square root of 242, you need to plug it in your calculator and you'll get 15.6. That means, if we come back up to this diagram, that we pushed this object 15.6 kilometers in this direction. Okay, let's try one more example. Let's use the example over here that I said. We're pushing it downward with a force of 5 newtons. We're pushing it to the right with a force of 5 newtons. And by the way, this is the net force of the up and down. Okay, and then this is the net force of the left and right. So it's not that I'm pushing it 5 newtons, it's that that's the net force of it going this direction. So I take both of my forces, I square them and add them together. That's going to give me my resultant force squared. So 5 squared is 25, and well, this is actually a -5, but -5 squared is still 25. And then this is also 25, and it's r squared. So then I have 50 equals r squared. So how do I get rid of the squared next to the r? Remember I told you in our previous problem, you just take the square root. So let's take the square root of r squared, and it's r. Whatever you do to one side, you have to do to the other. And so in your calculator, you're going to hit second square root and put 25, okay, just like this. And you press it in your calculator, and it tells us, oh, I put 25 in there. Whoops. I was like, that's not right. I got to take the square root, 50, I'm sorry, and it gives me 7.07. So that is my resultant force. That means my net force is actually 7.07 newtons in this downward and rightward direction. Okay, so we found magnitude. That's what we learned first. How do you find the magnitude of two forces going, one's going up or down and one's going left and right? But now I want us to practice finding the angle of that resultant vector. So, for example, we found that this box is being pushed 7.07 newtons in this direction, but I want to know the actual angle. So angles are actually measured from this X line right here. So the angle is actually measured all the way around here. So we're going to have a really big angle for this problem. So let me walk you through how we do that. What I want you to keep in mind is, let's say here's our angle. Okay, if this is the angle of our object, we're going to change A, B, and C to be, this is the adjacent side. It's this side that's right next to the angle, and it's connected to the 90-degree angle right here. This is going to be the opposite side of your triangle, and then this is the what's called the hypotenuse. So the long resultant end is your hypotenuse. That's your resultant vector. Your opposite vector will either be the vector that's to the left or the vector that's to the right. The adjacent vector is the vector going up or the vector going down. Okay, so here's an example. And by the way, we can use these formulas right here. You won't have to memorize them, you'll be given them. But we'll be using these formulas to find our angle. Okay, this is our angle, the sign for angle. Okay, these are buttons that we'll be using in our calculator. And the formula, I don't use A, B, and C, remember, so what I do here is sine is opposite divided by your hypotenuse. The way I remember that is SOH. S stands for sine, O stands for the number on the top of the fraction, and H stands for the number on the bottom of the fraction. So I think of this is a made-up word, so. And then cosine is your adjacent angle over your hypotenuse. So I think of this as cosine adjacent hypotenuse. And then tangent is opposite over adjacent. And so I think of TOA. So if you can remember TOA, then you can remember these formulas. So let's practice one. This is the same one that we had up above. Let's say here's our box, okay? It's being pushed 11 kilometers north and 11 kilometers east. The first thing we do is we need to find our resultant vector. It's somewhere right here. So how do we find a resultant vector? We end up squaring both of our forces, okay? And then we find our resultant force, which was 15.6 kilometers. Once we find this, we know all of the vectors that make up the triangle, okay? So we have 11 is the up and down. So the up and down one is called your adjacent. So this is the adjacent. This 11 is the left and right one, and the left and right one is called your opposite. So this is the adjacent. This is O, this is your opposite. And then this guy right here is your hypotenuse. It's the longest one, and it's 15.6 kilometers. So we have our A, our H, and our O. We can also just take these vectors and rearrange them. So the way you take these vectors and rearrange them is you always take your up and down vector and your left and right vector, and you put them together tail to head. Tails and heads have to touch. So I put the up vector like this. I know it's 11 kilometers. Okay, so I move that over here. My left and right arrow, I want this tail to be connected to the head. So here's the tail. It's connected to this guy's head. It's 11 kilometers. Okay. And then my arrow is right here. This is my resultant, which is 15.6 kilometers. So all I've done here is I took this arrow, okay, and I moved it upward so that I had a triangle here. Do you see this triangle? I just redrew it right down here. So you can take your vectors and create a little triangle, and you know what angle we're looking for here, right? We are going to be looking for the angle of this resultant vector. So we are looking for this angle. So the opposite, what is the vector that's opposite this angle right here? Our left and right arrow is opposite, and we already labeled that right over here. And then what's the vector that's adjacent? Well, it's this one right here because it's right next to the angle. And see how we already labeled it adjacent? All you have to know is the up and down arrow is your adjacent. And then the hypotenuse is the long vector. So we have all of these listed. So how do I find this angle? Well, we know all of our vectors. So we could use any of these formulas. So, ca, or tro, we could use any of these formulas to find our angle. This formula is helpful if you have your opposite vector and your hypotenuse vector. This formula is helpful if you have your adjacent vector and your hypotenuse vector. This formula is helpful if we have our opposite vector and our adjacent vector. Pretty much all the time, you guys will be given your opposite and your adjacent. You'll have an up and down arrow, and you'll have a left and right arrow. So typically, you're going to be using the tangent one. Because usually we don't have hypotenuse, usually we have to solve for that separately. So let's use our tangent. Okay, this one, we're not going to use this right here. So we want, here's our tangent, here's our angle, okay? and a tangent is opposite over adjacent. So what's our opposite? It's 11 kilometers. What's our adjacent? It's also 11 kilometers. So then our tangent of our angle is 1. That doesn't mean our angle is 1. I want to get my angle sign by itself. I want it to look like this. My angle equals blank. If you want to ever move sine, cosine, or tangent to the other side of the equation, you have to make the inverse of it. It's got to look like this, tangent -1. So if I want to move this to the other side in my computer, I'm going to type in tangent -1 and 1. I'm going to put 1 because this 1 is already on this side. So I open up my calculator, and you should see a tangent sign right here, and a cosine and a sine, and then right above it is the inverse. Okay, the inverse of tangent, the inverse of cosine, and the inverse of sine. So I'm going to press second and inverse of tan, and I put in 1, close my parentheses, and I get 45. So my angle is 45. Okay, it's a 45-degree angle. So now let's try another practice problem. Let's try this one here. You push a box 10 kilometers west and 5 kilometers south. Okay, so if I was to draw my free body diagram, I'm going 10 kilometers this way and 5 kilometers this way. I'm looking for this resultant vector, and I'm looking for the angle. So to find the vector, I just square both of my forces, and it gives me my resultant force. So I just type in all of these into my calculator. So 10 squared is 100, plus 5 squared is 25, equals r squared. And I add them together. Then I take the square root of both sides. So you take square root of 125, and it's 11.2. I'm going to round up. That's my resultant vector. So this resultant vector right here is 11.2 kilometers. How do I find the angle? Well, let's look at this angle. If I want to find the angle, remember you want to connect them tail to head. So if my resultant vector is going this way, what I want to do, I wonder if it'll let me do this. I want to take this arrow and move it because I'm trying to make my triangle, right? Now, since I didn't draw it perfectly, it doesn't look super great. But here's my triangle, basically, right? I want to find this angle. So to find this angle, you need to use sine, cosine, tangent, one of those formulas. So I usually use tangent. So my tangent is my opposite angle, which is my downward one. My downward one was 5 kilometers. It's opposite over adjacent. So my adjacent is my 10 kilometers. Okay, so that gives me 0.5. So what I have now is tangent of my angle is 0.5. I want to move tangent to the other side to get my angle. So 0.5, well, hold on. So when I move tangent to the other side, it's tangent -1. It's the inverse. Okay, and then I leave 0.5 there. So in my calculator, that comes out to, my angle is 26.6 degrees. Well, this is not my final answer. You need to keep in mind that I want the angle of the resultant vector. If you tell me that this resultant vector is at an angle of 26.6 degrees, remember we always start our angles right here, okay, on the positive x-axis. So if I'm starting my angle here and I go 26 degrees, 26.6 degrees, that means my vector is going this way. Well, we know my vector is going the opposite way. So if your vector is going this direction, like this, okay, the 26.6 degrees is only referring to the degree from this point on the x graph all the way to here. So it just takes a second for you to double check. Does this number make sense? Well, not really. What I need to do is I have to actually go 180 degrees and then go my 26.6 degrees. So I'm going to just add that number to 180. And then I get 206.6. So really, it's 206.6 degrees. So just check your answer and see if you need to add 180 degrees to it, okay, depending on where you're at. So let's do some another practice problem. So what we've learned is how to take this vector and produce the resultant vector. And the resultant vector's angle. But I want you to be able to go backwards too. If I give you the resultant vector and the angle, I want you to be able to tell me what were the components. Okay, what were these individual forces? So, for example, if I give you this problem, you should be able to tell me the individual vectors. So here they gave you the resultant vector. Okay, and they said the resultant vector is at an angle of 60 degrees. So all you have to do is make your graph and say, okay, where's 60 degrees? Well, you should know that this is 0 degrees, this is 90 degrees, this is 180, okay? And then when if you come all the way around, then it's 360. So basically, 60 degrees is kind of right here-ish. So go ahead and kind of basically graph it out. Graph out your 60 degrees. You know, this is 50, okay, and this is your hypotenuse, right? So let's label the other two. If this is your hypotenuse, what is this guy and this guy? See how I'm making it a triangle here? Well, if we're looking at this angle, this is our opposite because it's up and down. This is our adjacent because it's going left and right. So if we want to find opposite and adjacent, let's look at our formulas. The sine will give me opposite over hypotenuse. I have my hypotenuse, I have my angle, all I need is my opposite, right? So I could use this formula to find my opposite. Let's try cosine. Cosine is my adjacent over my hypotenuse. I could also do that too because I have my angle, I have my hypotenuse, I could find my adjacent. The only one that's not going to be very helpful is tangent. Tangent is not helpful when we're going backwards because guess what? You have your angle, but you don't have opposite and you don't have adjacent. So this one's not helpful to us. So let's find our vectors by using these two formulas. So let's start with sine. So the sine of our angle, what's our angle? 60 degrees, okay, is opposite, which we don't know, over hypotenuse, which we do, okay? So I'm looking for opposite, so I want to rearrange to solve for opposite. So I want to get the 50 on the other side. So let's multiply this by 50. So I have 50 times the sine of 60 is my opposite. That's not a 0, by the way. That's an O. So I just plug that in. 50 times, and I press sine in my calculator, and then I put 60 in parentheses. And my opposite vector is 43.3, and I think we're doing speed, so that's meters per second. That's my opposite. Now let's do the adjacent, right over here. So we're using the same angle, so it's 60. We're looking for our adjacent. We have our hypotenuse, it's 50. So I need to put 50 on either side. So 50 times the cosine of 60 gives me my adjacent angle. So I just plug that into my calculator and I get 25. So now I know all of my angles. It's 25 and 43, and I have all the information I need. So just to review, when you're doing your net forces, and we'll talk about this more in the next video, I want you to separate up and down and separate left and right, okay? Your goal is to get one up and down force and one left and right force, okay? Now, in the practice problems, I already just give you one up and down, and I give you one left and right. Once you have these, those are called your component vectors. Okay, your component vectors might look like this and this, or they may look like this and this, but you'll just get two component vectors, okay? And then you need to use this formula to find your resultant vector. Your resultant vector is always going to be your hypotenuse. Once you find that, you can find your angle by using those formulas that we talked about. And you can always go backwards too. So if I want you to find the component vectors, you can start by using this first and then go back and find your component vectors. So that's it for our video today. Go ahead and do your practice problems. Remember, you have to attempt all of them in order to receive credit. I will see you guys on Tuesday.